Assalamu alaikum, guys. This is continuation of our last class. So in our last class, we have actually did DSB double sideband, suppress carrier, coherent and non-coherent demodulation. So what we did in coherent and non-coherent demodulation, for example, in coherent demodulation. So let me provide you some correction to that lecture of coherent demodulation, which is actually this topic. Coherent demodulation. So here, while doing this demodulation of the double sideband suppressed carrier, I actually provided you this picture, right? So this picture actually is updated where we actually use all the capital notation, okay, instead of small letter notation. Here you see we used after demodulation we actually have two sidebands, this sidebands, and we have a baseband signal, which actually we can see here. This is actually our baseband signal and two sidebands here. Now what we did actually, we used a filter. We used a low pass filter to filter out, or sorry, to filter only the baseband. So if this is a low pass, so rest of the portion, I mean the sidebands, both of the sidebands will be omitted, because this is the low pass filter, right? The signal only passing through this low pass filter, and this portion of the sidebands, they will be omitted. This is according to the filter principle. Actually, I have noticed that in one of the last lecture or lecture in the coherent demodulation, I gave this explanation other way. Okay, so let me correct it here. So here we are using a low pass filter only to allow the base portion of the signal, or this portion of the signal, right? Okay. So when we actually did our non-coherent demodulation, means in coherent demodulation there was a phase equality between the received signal and the locally generated carrier. There was a phase equality between these two signals. If not, then we called it non-coherent demodulation, right? Which actually this portion of this lecture is actually here. There we actually add a carrier offset as a phase as a carrier phase offset to be added in the locally generated carrier, and we actually see there that if the phase offset is not equal to 0, then what happens is actually we deduce a receive signal where actually we find a baseband signal and two sidebands where this phase offset is included, which was not present in the previous case. So there, from this baseband, because this is the only portion that is filtered out by the low pass filter, this portion will be omitted. So that's why actually we consider the power of this square of this equation actually gives you the power. So we actually only took the power of this baseband signal. Okay, output power, which is actually there. And we actually also we actually shown that if this phase offset goes up to pi by 2 or 90 degree, then we have seen that this power becomes 0. This power becomes 0 means as phase phi increases, the output power of the demodulated signal decreases, and it goes up to 0 if the difference between the two signal, the receive signal and the phase offset, there is a angle difference is 90 degree, means this signal becomes orthogonal, then your the receive power becomes 0. That's actually we have seen in our previous lecture. So we'll actually continue from here. Okay. So let me remove all the edited stuff I have added just now. So okay. So today's topics of the today's lecture is a phase offset. So let us write what whenever. So let us write the signal we received as a phase non-coherent demodulation. So what signal we received? So we received signal AC MT cos 2 pi FCT. Now this signal we actually, this is called our incoming signal, right? Incoming signal. So this signal will be multiplied. How we multiply? We actually use a mixture, which actually we have shown here, right? The incoming signal comes and actually it multiplied with our phase local oscillator or locally generated carrier, which have a phase in non-coherent demodulation, right? So which will be multiplied by the cos 2 pi FCT plus this pi, right? So these are the locally generated. This portion is a locally generated carrier. Now, after this pass through, after this signal pass through a low pass filter, then we only have a baseband portion of the signal, which is actually half AC MT cos theta. Sorry, cos phi. Because other portions of the signal, they are actually filtered out by the low pass filter. Low pass filter only allow the lower frequency of the signal, which is actually the baseband signal in our cases. Okay. Here the extra factor encompassed to the coherent demodulation. Here you see this phi is the extra portion. So this phi, this is actually the extra portion compared to our, this is actually extra. So extra compared to, or extra factor actually, factor compared to no coherent demodulation. Coherent demodulation. Okay. So this is the phi actually added. So in coherent demodulation actually this phi becomes 0 degree or whatever. Okay, so this cos phi, sorry, the whole cos phi term is actually extra compared to the coherent demodulation, because this is actually the non-coherent demodulation that we are actually dealing with. Okay, and we also have seen that the resulted power, the power which is actually square of this signal, which is 1/4 is c square, and mt, actually mt square becomes pm in our previous equation. So we actually already know this term, and cos square phi. So here we can see that as phi or phase offset increases from 0 to pi, output power decreases to 0. So we can say that as phi or phase offset increases increases from 0 to pi by 2. 0, this becomes, you see here, cos 0 degree, right? Cos 0 degree becomes 1, becomes as 0, it gives you the maximum power. At pi by 2 is cos 0, cos pi by 2 actually 0. So which makes the whole term, the whole power term actually 0. Okay, so it increases from 0 to pi, the output power, or actually it's actually the receive power, output power or receive power decreases to 0. Okay, so it's a very serious issue. If this phi keeps increasing up to pi by 2, then the power or receive power tends to 0. So this is actually a serious issue in a communication system. So let us see a scenario in a communication, why this happens and how to counter it. Okay, let's say give a scenario. Say this is a mobile tower. So this is actually a mobile, or we called it baseband, BTS, mobile tower. This is a mobile tower. Or we also called it base station. In communication, we call it base station. Now, imagine you have a mobile phone, or you are a user having a mobile phone. Okay. So now in this mobile phone, how the base station actually connects from the tower? Probably there are some microwave links or microwave antennas. Probably you've seen these antennas. From this antenna, the signal comes to this user antenna, isn't it? That's the way we actually, our mobile phone or cellular system works. Okay. In a fixed transmitter and receiver, this is not a problem. But in a mobile environment, this phi issue is a serious issue. We will actually see why this is a serious issue. Okay. Now, from this tower, for example, this is a transmitter. Okay. So what the transmitter transmits? Say transmit signal. So transmit signal xt. So transmit signal is, say, xt. So AC mt cos 2 pi fct. So this is a signal that's transmitter transmit. Here, because this is a wireless environment, what is the propagation delay? Propagation. You see, there sometimes takes place to transmit this signal from this distance to this distance, right? So what is this propagation delay? If this distance becomes d, then propagation delay is nothing but d by c. What is this c? C is the speed of light. Speed of light. Okay. So we are actually trying to understand a mobile environment. Okay. So because in this mobile environment and there is a propagation delay, so the signal which is actually transmitted at xt here at the transmitter, the signal is xt, will be received here as a yt. This yt, so this yt signal or the received signal in the mobile is nothing but the xt signal, the same xt signal, but a delayed version. Because of this propagation delay, the signal will be a delayed version. Here, this tau is the delayed version of this is the delay amount. So this xt minus delta is actually the delayed version of xt. This is a delayed version of transmitted signal xt. Okay. Okay. Say, okay. So if this is the case, then what is this? If this is the case, then what is our this signal? This signal. Okay, this signal. What is this signal? We write it. Okay, so this is the case. Okay. So what will be the xt? So xt. So what will be the xt minus tau? It will be ac. So ac m t minus this tau. If x t is for this one, so we are adding actually a delay amount. So everywhere this delay amount will be added. Okay. Okay. So cos 2 pi fc t minus this tau. Okay. So we can write as c m t minus tau cos 2 pi fc t minus 2 pi fc this tau is incorporated here. So we already know what is this delay tau. It's actually here this tau. So tau is nothing but d by c. So we can add it here. fc minus tau cos 2 pi fct minus 2 pi fc. Tau is nothing but the d by c, which actually we get it here. Okay. This portion twice pi fc d by c, this is actually nothing but this phase offset. This is nothing but the phase of this offset in our cases. Phase offset. Phase offset. Okay. So we find that 2 pi fc d by c is the phase offset. That is actually now here you see m t minus tau. Now we can did little bit more modification assumption here that so here we actually do some assumption that we know the frequency of message signal is much smaller than the frequency of the carrier. Means the change of the frequency, the frequency change in the message signal is very slow, or the MT message signal MT is very slow. The maximum frequency component f m of the message is much lower than the that is compared to the fc. That's why actually we can actually write a c is almost here. If this is the case, where the frequency of the message signal is much lower than the carrier, then m t minus tau is almost same as mt, because of the maximum frequency component or fm of the message signal is much lower compared to the fc, the carrier frequency. So we can write this as a as equivalent. Okay. Okay. So this one we can write it like this. So the remaining equation will be same. Here actually we have just seen we actually have a phase offset here. Okay. So we can write it as a cos twice pi fc t minus this phi, which is actually a function of d actually here, right? So this phi is the phase offset, which is actually the function of d. Now we know that this phi, this phi is nothing but 2 pi fc d by c. This one 2 pi fc D by C. Okay. So what we are trying to say that varying phase offset, which is phi, which is a function of the distance d of the user. So we can actually, regarding this one, we can say that d is a, here in our mobile scenario, the distance, this d, this user is a mobile user, right? So it's roam, this user is roam around. This is the user, this is the user, mobile user. So this user moves around here and there, here and there. Okay, so if he do this, then d also changes. Means actually the phase also has to be changes, because the phase, this phase offset is actually a function of d. So what we can write is that varying phase offset phi is a function of distance d, or function of distance of the user, distance d of the user, or mobile user, whatever. Okay, so this is a function of the mobile user, d. Okay, now we like to play around with this distance function. Okay, let's see what happened. So what is so this phi as a function of d, let's differentiate it d by dt. What will happen to this one then? So d by dt of 2 pi fc d by c. Okay, so d by dt, this will be only effect for this d. So we can write to other portion will be the constant fc by c. So d by dd differentiate by dd by dt. So what is this? This one. You see, this is the change of distance with time, isn't it? D by dt. What is the change of distance in time or part time? It's actually nothing but the velocity, isn't it? So this is actually the velocity. Velocity of who? Velocity of this user. Velocity of the mobile user. This one. This guy. Velocity of this mobile user. Okay. So, and what is this one? What is this value? This is actually nothing but the rate of change of the phase offset, isn't it? This is the rate of change, because it's d by dt. So it's a rate of change of what? Of the phase offset. Rate of change of phase offset. Phi. Phase offset. Right? Okay. So what we can this amount is a constant. Right? So we can interpret this whole stuff. We can interpret the whole stuff as varying. So varying distance gives us the varying delay. Which ultimately gives us the varying phase offset. what actually we're trying to say, that as this user roams around here and there, this user roams around here and there, so its distance d keeps changing, right? This distance keeps changing. Because of this varying distance, we will get varying delay, because this d changes, the delay changes, which ultimately gives the varying delay is nothing but the varying phase offset. Varying delay is nothing but the varying phase offset, which is because varying delay, this phase offset is a function of d, so varying delay gives us a varying phase offset. Okay. Okay. So what we can say, that now we can say, to avoid the performance degradation, you see here we have seen in our previous okay, that as phase phi or phase offset increases, it will actually ultimately affect to our receive power. Means varying phase offset ultimately affect our receive power. Means the varying delay ultimately affects our receive power. Means the varying distance ultimately affect our or deteriorate our receive power. So what we can write, that the to avoid the performance degradation, actually if we receive lower power in the receiver, which actually ultimately gives us low performance, right? So to avoid the performance degradation, one has to frequently synchronize the phase of the local oscillator with that of the incoming signal, right? Why this phase offset occur? Why this phase offset occur? Because there is no phase synchronization between these this incoming signal and the locally oscillated carrier. There is a phase offset occurs. So to avoid this issue, that or to avoid the performance degradation, what we have to do, we have to very often the locally generated carrier should be synchronized with the incoming signal. Okay. To avoid, so we can write, so what we can write, to avoid performance degradation, one has to frequently synchronize phase of the local generated or local oscillator. Actually locally generated carrier. Actually we should lay locally generated carrier. Locally generated carrier. Actually, this locally generated carrier is generated by the local oscillator. So locally generated carrier synchronous phase of the locally generated carrier with the incoming signal. So with the incoming signal. So this process is called phase synchronization. This is called phase synchronization. Okay, so what we are trying to say, that this guy, the mobile user, he actually roams around So because his roams around, so distance keeps changing. Because of distance keeps changing, propagation delay also keeps changing. Because of the propagation delay keeps changing, then ultimately the phase, the offset, phase offset also keeps changing. So, and that also gives us the performance degradation. So what we have to do, the locally carried generator, but frequently they should be synchronized so that this phi impact of phi becomes keeps low. Okay, which actually ultimately will give you a very good performance. Okay, so how this phase synchronization can be done, right? So we can conclude that okay, there is a phase synchronization is needed. Phase synchronization is needed. How this synchronization is done? Okay, so it will be done by a receiver. So that receiver is called this will be done by a receiver, a special kind of receiver. It is called a Costas receiver. Or this is also called Costas loop. We'll also discuss about this receiver in this lecture also. Okay, so we concluded that for maintaining phase synchronization, we need a Costas receiver or a Costas loop. So let's see how a Costas receiver or Costas loop works. Okay, let's draw a schematic diagram of a Costas loop. So draw a schematic diagram. So schematic receiver. So let us draw a schematic diagram of a Costas receiver. How it looks like in schematic. Okay. So we already mentioned that Costas receiver is needed for phase synchronization. So let's see, we receive our signal as xt, which is actually nothing but AC mt cos 2 pi fct is the signal we are receiving. So the received signal is divided into two parts. So each of the part goes to a demodulator. So each of the part goes to a demodulator. Each of the part goes to a demodulator. Okay. In the for example, this is upper part, upper, and this is our lower part. So each part goes to a demodulator, and these demodulator are driven by a VCO. VCO. So what is VCO? VCO is called, what is VCO? Is called voltage control oscillator. Voltage control oscillator. So each of the demodulator are fed by a VCO. With which frequency? With this, the cos with the locally generated carrier, with the locally generated carrier. So which is actually our cases cos 2 pi fc e plus this offset of phi offset that we actually seen in our non-current demodulation. This phi is introduced, right? Okay. So other part of this VCO goes to a phase shifter, where is actually it becomes a pi by 2 phase shift occurs, which actually ultimately will go to this demodulator, right? So in this demodulator, this signal, this locally generated carrier is actually phase shifted, which actually will become, eventually it becomes sine 2 pi fct plus theta. Okay, the output of both of these, output of the both of the uh, output of the both of the demodulator pass through a low pass filter. Low pass filter pass through a low pass filter. Low pass filter, and the output of this low pass filter eventually met with a frequency discriminator. We can call it as a frequency discriminator, or actually this is a frequency multiplier also. Sorry, this is a phase discriminator. The phase will be detected here. Phase discriminator. So the output of this phase discriminator actually will ultimately goes to the, whatever the output comes, based on this output, the VCO, voltage control oscillator, will actually manipulate or change this phase offset. Let's see how it works. Okay, let's see how it works. So for upper term, the signal which is actually received goes to the upper portion and multiplied with the this one. So for upper portion, upper, what happened? So AC MT cos 2 pi FC T, this will be multiplied with the our locally generated carrier, which is actually cos 2 pi FCT plus phi. Okay. Okay. What is the so if we solve it, we solve it earlier, right? When we discussed about only the phase non-coherent demodulation actually. So we already know the result. So I'm not deriving it again. So let us write AC by 2 MT cos theta cos phi by cos 4 pi FCT plus phi. Here we have seen that this is actually the side bands, right? In or the component at frequency component at 2FC. Remember, it was 2 pi FC, so FC becomes again 2FC. So this was the center frequency, which is actually this one for that component, right? Okay. So we eventually know the low pass filter version. So if this signal passes, so you see this signal, this will be at the output of this low pass filter. So after the low pass filter, after low pass filter, what we have? We have only this portion of the signal, which is actually multiplied by with this one. So SCM T by 2 cos phi after the low pass section, upper low pass filter, right? Okay, so this was the for the upper section. Let's find it. What is the for the lower section? Okay, so this is for the upper part. So what is for the lower? What is for the lower section? Means actually this signal is goes through this lower part to the lower demodulator, where it actually multiplied with the sign instead of cos. So what is the signal becomes? The signal becomes ACMT cos 2 pi FCT. This is actually our incoming signal. Now this time it will be multiplied by the sine, which is actually this part sine. So sine 2 pi fc t plus phi. So again, I'm not solving it. So what we will have, we'll have AC t by 2 sine phi plus sine 4 pi fc t plus this phi. We know that this part is actually the component at twice of fc. Now after low pass filter, so after low pass filter means after like this signal and this signal, when they multiplied and these are passing through the low pass filter, after the low pass filter, then this portion only will remains with sine. So after low pass filter, the signal will be AC t by 2 sine theta. So both upper and lower part, the low pass filter, the signal from the upper part, and from the lower part, they are mixing with the phase discriminator or phase multiplier, right? So let's see what we have it. So the output of the phase discriminator. So the output of, if this signal, two signal come to the phase discriminator, what will be the output of this phase discriminator that we want to order? Phase discriminator is also called a phase signal multiplier or phase multiplier. Okay. So output of the phase discriminator, or we can say phase discriminator. Okay. What is the output of the phase discriminator? Which is actually nothing but the multiplication of these two part. So which is actually nothing but AC mt divided by 2 cos phi multiplied by AC mt by 2 sin pi. So we have actually, so this part will be square. So AC square m square t by 4 sin phi cos phi. Okay, so this is actually our output of the phase discriminator. So from where after this, the output of the phase discriminator, this one actually eventually is inputted, right? Inputted to the VCO and the voltage controlled oscillator. Okay, so based on the these values, these phi values, the phase discriminator will actually tune accordingly. Now, how these so okay, now we do some assumption. Okay, so let's do some assumption. Now, how this VCO will work? Okay, let's do some assumption. Okay, let us assume that this is actually our assumption. So we are assuming that phi is small. Assume the phi is small if this is the case, because you see the phase offset will not actually vary much. All right, we know why this phase offset comes. This phase offset comes because of the mobility of the user who moves around, because of the distance from the transmitter changes, and because of that the delay changes, and that's why the offset occurs. So of course this offset will not be very bigger value. So we assume that phi is small, so it will be typically minus pi by 2 to pi by 2. it should be varying within this region. If this is the case, then this is the range. So this can be that means the phi can be a positive value or the phi can also be a negative value. Okay, say if this phi is positive, then what we have? We have the phase discriminator. The phase discriminator, what we have? This value, this one. So let us see. So a square m square t. If this is a phase is a positive value, okay, and this portion is a constant, which is actually usually positive, like tends to be positive. So cos phi and both the sin phi both will also be a positive. Means the whole value will be a positive. The if phi is a positive value. Okay, if otherwise, if not, what happens? If phi is a negative value, then what? If phi is a negative value, then the phase discriminator output will be what? And so this is actually phase discriminator output. Output. So phase discriminator output. So we can write the phase discriminator output is this one. If phase is negative, then phase discriminator output. What happens to this phase? So a square m square t by 4. Of course, this becomes a constant value. This is actually so cos phi and sin phi, right? If phase is negative, then this one is of course a positive value. It's also positive value. So cos phi, this will also, even the phi is a negative value, cos phi is eventually a positive value, but sin phi, because of the negative phi, sin phi will be a negative. Okay, so we can actually summarize it. We can write it. We can summary here that if phase discriminator output is greater than 0, which is actually this case, then phi is phi decreases. Phi so if okay, phi. So if phase discriminator output is less than 0, which is the this case, then phi actually increases. So what we are trying to say here, that the voltage control oscillator VCO, actually the VCO is configured such a way that is configured in such a way that if the phase discriminator output is greater than 0, which is actually this case, this 0, then it is designed, the VCO is designed in such a way that it reduces or decreases the phi here. It actually reduces the phi here, because if what I am saying is that if the phase discriminator value is positive to the VCO, then VCO actually reduce the value of phi. That's actually what I'm saying here. Okay, so the VCO is configured such a way that if phase discriminator output is greater than 0, which actually the VCO actually decreases the phi. In other way, if the phase discriminator output is less than 0, which actually the negative, then the VCO is reason is such a way that it increases the phi. You see, it keeps it balanced. Means actually, if the phase becomes larger, then the VCO make the like next instant phase as a lower value, and if phase is a negative value, then in the next instant immediately VCO makes the phase to rise. So it always keep the phase in a in a in a in a fixed value. Okay, it minimizes actually. It keeps minimizing. So in other way, we can write that in other way, the same statement we can write in other way, that positive phase makes it decreasing in phase. Decreasing in phase in the VCO, huh? And in the opposite, in negative phi makes it as a increasing in phase. Increasing in phase. So the negative phi make it as increasing in phase. So ultimately, by doing this, the phase is actually remains in 0. So synchronization is achieved between the locally generated carrier and by this synchronization is maintained. So by this synchronization is maintained by the incoming signal and the locally generated carrier. So so what we can see from the figure, that whenever the phase detector value is positive, is actually driven the phase negative. If phase discriminator output is positive, it actually drive the phase as a decreasing value. Okay, if this value is higher, phase value is like positive, it makes the phase to be down, or if the phase synchronization discriminator is value is negative, then it's actually driven the output of the VCO as a positive, so that the phase keeps remain in a the phase offset remains in a 0. That's actually this VCO voltage control oscillator do. So if it receives from the phase discriminator as a positive value, it decrease the phi, and if it receives a negative value from the phase discriminator, and it increases actually this value of phi. So it always tries to keep the phase in a minimum, ultimately 0. So the phase synchronization is maintained. So we see if in a roaming scenario, that actually we have seen in a roaming scenario, when the user is keep changing its position, ultimately changing the D, which actually ultimately changing the delay, which ultimately creates a larger phi, which actually will eventually decrease our receive power. This phase synchronous keeps this phi value always minimized, so we are always in a we always receive the better receive power, highest or maximum receive power. So that's actually the job of the Costas receiver. So here ends our lecture about the Costas receiver. Thank you. Assalamu alaikum.